So, we will return to our discussion on cycle based simulators. So, just to give you a recap, that we started by studying two types of simulators. One was event driven simulators, the other was cycle based simulators. The essential difference between the two was that in event driven simulators, we whenever any input change takes place, we immediately propagate the event through the gates and the flip flops, and as a result all the intermediate events that take place, including minor transitions and glitches, etc., they are all captured in the event driven simulation process. The flip side of event driven simulation was that because we are propagating all the events, so it is quite possible that the same gate gets evaluated many number of times during the simulation process, and that is because the different events pass through that gate at different points of time. Then we move to cycle based simulators, which are motivated by the fact that most of the designs that we simulate are digital designs, where the steady state value of the circuit is latched onto the flops in every cycle. So, the intermediate values that the signals take between two cycles is not important. What is important is when the circuit stabilizes, at that point of time whatever values are the values of the signals, those values are latched into the flops. So, if that is the objective, then it is not necessary to propagate each and every event through the gates, rather we can evaluate everything based on the steady state values. Right. Now, in cycle based simulators, therefore, evaluations of all intermediate events are not performed, and each gate is evaluated only once in each cycle. Then we saw that in order to do this thing, that we want to evaluate every gate only once, we need to topologically order the circuit, in the sense that we should not start evaluating this gate before we have evaluated this gate, because if we first evaluate this, then the output of this gate might have changed in this cycle. So, we will again have to simulate this, right. So, even though some event might pass through this before this gate stabilizes, we will wait for this one to stabilize and then simulate this, right. So, then we studied the topological ordering algorithm, by which we levelize the circuit, in the sense that this is the first level, this is the second level, and this is the third level, and then we simulate the gates from one level to the other, right. And we studied the topological sort algorithm for doing that levelization. Right. Now, let us come to the way that RTL code is scheduled for cycle based simulation. So, let us look at this circuit here. So, this circuit here has a always block, right, up to here, and then it has two assign statements, and then there is a structural block, which is some kind of gate, right. Now, typically in a RTL circuit, we are going to have these three types of things. We are going to have some structural components, which are gates, modules, which are defined at the structural level. We will have some behavioral components like this always block, and we will have some assignment statements like this, which are continuous assignment kind of things. They are done every time. Now, the sequence in which the simulator is going to work is like this, that it is going to process the always block first, right. So, remember that typically these always blocks will be guarded with some condition, like at passage clock, right. So, this is not a necessity, you can have always blocks which do not have any guard condition. So, whatever happened in the previous cycle can trigger some of these guard conditions, right. So, for example, when the clock transits, then that transition of the clock can trigger some of these always blocks. So, we first look at the always blocks. Now, many of them might have got triggered. So, we take their codes and we first execute that. Now, within that code there can be these non blocking assignment statements. Now, these non-blocking assignment statements will not be processed first. They, by definition, they will be processed at the end, right. Similarly, these statements like strobe, which are actually going to print or monitor the output of the circuit, these are also going to be taken up at the end of the simulation cycle after everything has steadied down, right. So, besides these, the rest of the always block will be executed first. Then these assignment statements will be taken up, and at the end the structural block will get executed. So, this is the sequence that is followed. So, if you look at the order of execution of these statements, then this is how it is, that this A equal to B is executed first, then we skip this one because this is going to be done at the end, then this will get executed. This is a PLI call. PLI is a programming language interface through which you can run your own functions. So, this is getting called here. Then you have this statement. See, this is again relegated to the end. So, we have this one which is getting simulated after this. Then we have the continuous assignments, these two. Now, these two can be executed in any order. So, this followed by this or this followed by this, does not matter, and then the gate will be simulated, right. Now, after all this has been done, then we process the non-blocking assignment statement, right, and finally the strobe. All right. Now, having seen the way that the events are processed, we now have to look at another interesting thing. Is in a cycle based simulation, the clock is very important, right, because we are simulating everything in a clock cycle, right. Now, as you have seen in the previous code, that clock, that always blocks can be triggered at the edges of the clock, right, at passage clock. There could be another always block which is triggered at the neg edge of clock or the negative edge of the clock, right. There can be a block which is triggered at clock, which means that whenever clock changes, does not matter whether it is a passage or neg edge, then it is going to get triggered, right. So, when there is a positive edge of the clock, those always blocks which are triggered at the neg edge of the clock will not get simulated, right, and vice versa. So, we come to the question of clock domain. Now, clock domain analysis is important because clocks can have more than one type of event like passage, neg edge, etc., and we do have lots of circuits which have multiple clocks. Now, coming to the question of multiple clocks, there can be multiple clocks for a variety of reasons. One is that we have clocks derived out of another clock, which means that we have one clock, we half that clock, right, to run some part of the circuit at a speed which is faster, right, and the rest of the circuit runs on the slower clock. So, it may be that one clock is derived out of the other. There are also times when we put a phase lag in the clock. You know why? Now, there are several problems that come up. Let us look at a reasonably large combinational circuit here, right. This is going to take some amount of time to stabilize. Now, the clock is feeding into this, right. Now, the output of this one, right, is going to feed into another block. Now, this one also has some clock. Now, there is a latch here where I want to latch some output of this combinational logic, right. But it may so happen that by the time this output becomes available by passing through this big combinational logic, this clock has already latched whatever data that is there, right. So, we did not have time enough for the propagation of this. So, you may actually want to put some kind of buffer here to slow down the clock. So, the pulse that comes here comes at certain point of time, and this one comes a little bit later than that, right. Sometimes this is intended, and sometimes this happens because the clock path is so large that even if you do not want a delay, there is a delay in the clock. So, which is called a clock skew, right. In any case, what this results in is that in your domain you can have multiple clocks. Another very convincing reason for having multiple clocks is when we have power domains. Now, as you may know that power is a very important design criteria. Most of the circuits that we design for portable devices like cell phones, laptops, etc., have to be optimized for power. So, to optimize for power, what people do is you take the whole circuit and then different parts of that circuit is broken up into what are called power islands. These are called power domains. Okay. Now, what are power domains? The idea is that we know that when one block of the circuit, one power domain is active, we may know that at that time some other power domain is not active, right. So, if some power domain is not active, in other words there is no computation that is going on here, then we can reduce the power of this because it is not doing anything, right. Now, there are various ways of cutting out the power. The simplest thing is that simply shut off its power line, no? But that is a drastic action. Why? Because this part of the circuit has some state, right. So, it has some flux in it. Now, if you completely shut off power, the state will be lost because these are all volatile memory. If you remove the power, the state will be lost. So, you do not want to, you may not want to completely shut off the power, you may want to retain its state, but still make it operate at a very low power. So, one option is reduce the voltage level, let it operate at a lower voltage level. Another option is reduce the clock speed, slow it down. Why? Because there are two components of power consumption. One is called static power or leakage power, which you cannot avoid in this case unless you completely shut off the power. The other is dynamic power, and that dynamic power is that as the circuit makes transitions, certain signals are changing from on to off and off to on, that consumes power because you are charging capacitors, the gate capacitors, discharging them all the time, right. So, if you slow down the clock, then the power consumption is also going to slow down, right. So, you reduce the frequency of the clock in the domain which you want to put in, not complete shutdown, but in a low power state, right. So, that is another reason why you will have clocks which are operating at different frequencies, right. So, in the simulation perspective, when a circuit has multiple clocks, not all logic has to be evaluated at every clock transition. We have to determine the part of the circuit that requires evaluation at each clock transition, and this task is called clock domain analysis. So, in simple terms, a clock can potentially have two clock domains, one for a rising transition and one for a falling transition. This is because flip flops and latches may be sensitive to rising or falling transitions of the clock, right. Now, the tricky part in all this is the latches, because latches are can be level sensitive. You know what we mean by level sensitive, right? The latch will record its data when the enable signal is in a particular value. So, for example, if I have a latch here and if I have a enable signal which is high enable, that means that when enable is high, at that time whatever data that you put here, that is going to appear here immediately. In other words, this becomes transparent when enable is high, right? When enable is low, then it holds its previous value. So, if I lower D and then lower enable, then the value of Q will be 0. It is going to get latched at 0, right? As long as enable is high, if I pass some signal through D, I will see the same signal at Q, because it is just acting as a transparent latch. Is that clear? Right. So, when we do clock domain analysis, then we have to determine that that for a particular event of the clock, is the latch transparent or is it opaque? Okay, that is what we have to determine. So, let us see how we go about doing that. So, this is a clock domain partitioning algorithm. Identify all flip flops and latches triggered by the clock C. So, remember that there can be different clocks in the circuit. So, we just follow the clock and see that which are the flip flops and latches that are driven by that clock. For a flip flop or latch, backtrace from its input until it arrives at a primary input or a flip flop or an opaque latch. Opaque latch means that latch value is not going to change for the given value of the clock, right. So, when the enable is low, for in our example, at that time the latch becomes opaque, because whatever value it is holding at that time is static, it is latched onto that, right. We will see examples of this. So, we backtrace from the flip flop or latch until it arrives at a primary input flip flop or an opaque latch, and the traversed logic is part of the clock domain. We repeat this. So, this is the most important step, and then we repeat this step for each of the flip flops and latches, and the union of all traversed logic of positive triggered flip flops and low transparent latches is called the rising clock domain, because these are triggered by the positive edge of the clock, and the domain for the falling transition of the clock is similarly defined. Right. So, let us take an example which is going to make this more clear. So, here is a example where you see that we have these FFs are the flip flops and C1, C2 are the two clocks. This G3, G6 are two they are two latches, okay, and G2, G4, G7 are gates, logic gates. Now, let us say that we look at the rising transition domain of clock C1 for G1. Okay, so, the rising transition for clock C1, all right. So, to find out the clock domain for the rising transition of C1, we first identify that which are the flip flops which are triggered by the rising condition of C1. So, we find that G1 is 1, which is triggered by the rising clock of C1, right. Let us look at the other two flip flops G5 and G8. They are both triggered at the neg edge, because you see there is a knot here. Okay. So C1 is the one which is triggered by the rising clock. G6, yeah, that's a latch. That's a latch. We are going to come to that later, right. Now this one is in the rising clock domain. So now to find out that in the rising clock domain which is the portion of the circuit that we need to simulate, right. So we backtrace from this. So backtracing that takes me to this logic gate. So this logic gate has to be simulated. We go further back and then we come to this one. Now the question is that is this latch transparent or opaque at this point of time? In other words, do we have to look beyond this latch or not? So now let us see, when we are talking about the rising clock for C1, when C1 is rising, at that time what is the value of C2? At that time the value of C2 is 0. See, whenever C1 is rising, C2 is 0, right. If C2 is 0, then this enable is enabled, because C2 is 0 and this is passing through this knot. So this latch is enabled. When the latch is enabled, any change in the inputs is going to ripple through, because the enable is high, so it is going to ripple through. So this latch is transparent at this point of time, right. So we need to look also at G4. When we look beyond G4, let us look at this flop. Now at the positive edge of the clock C1, this one's value does not change, it remains steady, because this is triggered by the negative edge of the clock. So at the positive edge of the clock there is no event that is going to take place here, right. So we conclude that this yellow portion is the rising transition domain of clock C1 for G1, right. Is that clear? For this here also, yes. So when we look at this one, we find that the same is the case for this one, because the flip flop G8 is also triggered on the negative edge of the clock. So this is also a steady state value, right. Is this clear? Any questions about this? Now let us look at, so this says that this latch is transparent in this domain because C2 is low when C1 rises. Now this one is the clock domain for a falling transition of C1, right. So here we were looking at the rising transition of C1. Now let us look at a falling transition of C1, right. Now when we are having a falling transition of C1, at that time this one will latch its value, right. So see, this is a latch which is enabled by C1. As long as C1 is high, it is like a wire, it is not latching anything. Now when C1 falls, at that point whatever value was there in D, that is the value which is going to get latched in C1. So in the falling transition of C1, we need to evaluate the cone of logic before this, because that is the value which is going to get latched in this latch, right. So in order to evaluate that logic, that is at the falling transition of C1, we know that G7 we have to evaluate. So we propagate back from G7. Now look at this one. So this is a flip flop, right? So again, whatever is the value that is available here, that is going to be taken here. Now let us look at this latch. Now this latch, let us look at the falling transition of C1. When C1 is falling, at that time C2 is high, right? When C1 is falling, at that time C2 is high. If C2 is high, then this latch is not enabled at that point of time. So it's like a flip flop at that point of time. Its output is steady, it's not changing. So we treat this as an opaque latch at that time. So the only thing that we have to evaluate is G7. We take the steady state value of Q here, we take the value that is present here, simulate G7, produce the value of D, and that's the value of D that is going to get latched when C1 falls. This clear?
So G8 is also the transition during the low transition of the clock.
Yes, that's a good question. Now let us see what we do about that. See, the question is that the question that he has asked is that when C1 is falling, this is a negage of C1. This one latches its value at the negage of C1 because this is a negative edge triggered flip flop. So what value do we take here for simulating G7, right? So now by the simulation semantics of Verilog, when we and by the simulation semantics of cycle based simulators, when we are simulating the value of one cycle, the flip flop values that were there already are the ones which are taken here for the flops. So if the value here was 1 at that point of time, then we are going to take 1 only, not the value that is here, because the idea is that you evaluate everything, and when the actual transition takes place, you just update all of them together. So it is not as if that this edge produces the value and then that shoots through, right? The idea is that everything that you have here is first evaluated. So the inputs of all the flip flops that are triggered on that clock are evaluated based on the previous values or the steady state values, and then when the clock comes, then all of them get latched at the same instant. Okay? That is the semantics of cycle based simulation. Okay? Now you might feel that what will actually happen in the circuit. I mean, is it possible that it is going to shoot through, right? If it does shoot through, then that's a race problem, and we do have mechanisms in the circuit to prevent that from happening. Right? And people use different kinds of tricks. It could even be that you have alternate passage and negage triggered flops. You don't put a set of positive edge triggered flop cascaded after one after the other. So there are various kinds of tricks that people use. All right. So now, yes, any questions? Now we go to hybrid simulators. The simulators which are going to use different types of combinations of compiled and event driven simulators. So one is compiled event driven simulators, where we do the following thing: components of the circuit are compiled code. Okay, the components of the circuits are compiled code, and triggering the evaluation of a component is dictated by the events among the components. So, in other words, what we are doing here is that in pure event driven simulation, we are propagating the events through the smallest granularity blocks. So, we are saying that we will evaluate the events through each and every gate. What you might alternatively do is do this event propagation at a coarser granularity. So, you say that this is my combinational logic 1, this is my combinational logic 2, right. Now, these have certain inputs, this has certain outputs, some of these outputs may be feeding into this one, right, and I have some combination logic 3 where some of this might be feeding in. Now, we say that this we treat as a single unit. So, we will not propagate events within this combinational logic, we will treat this as a single compiled code. Given the inputs, we will find out the outputs. Now, then we will see that whether any of the outputs of CL2 is changing. If none of the outputs of CL2 is changing, then by following the event driven paradigm, we do not simulate CL2 at all. But if we find that one of the inputs of CL2 is changing, then we simulate the whole of CL2, treating it as one black box, right. So, that is what we mean by compiled event driven simulators, right, and this works really well. I mean, you can have parts of the logic which are evaluated using other techniques. For example, we did some work on one of the industry standard simulators, where we took much of the arithmetic logic and then replaced them by word level functions. For example, you have a bit level multiplier. Okay, we do a verification and find out that it does multiply correctly. Now, once we know that it is a correct multiplier, we do not need the bit level implementation at all. We just can write one line of code saying that C is equal to A into B, right, and then make the simulator only simulate that high level line, right. So, that speeds up the simulation quite a lot, because rather than simulating each and every gate at the lowest level of granularity, you can do that at a much coarser. Then leveled event processing for zero delay simulation. This is another trick which is used very commonly. So, if there is a part of the logic where you want to do zero delay simulation, in other words, you are not interested in the delay of the circuit. So, then what you do is you topologically order that part of the circuit and do it just like you would do it in a cycle based simulation. So, any part of the circuit which you want to treat as zero delay, there you do this kind of topological ordering and evaluate it, right, rather than doing a complete event driven simulation. The difference is that cycle based simulation will evaluate all the circuit components, whereas when you are doing levelized event processing, then we will only evaluate those gates which has input events, right, but we will do that in a topological order, so that one gate is not simulated more than once, right. If you have delays, you cannot do that. Now, is that clear? If you consider delays, then you cannot think of topologically ordering the gate and hope that every gate will be simulated exactly once. It is going to work only if you are looking at the zero delay model. So, if you cannot see why it is so, please spend some time thinking on that. Right? This levelized event driven simulation will work only for the zero delay model. It is not going to work for any other delay models, right. The other important thing that we need to look at is how do we handle combinational loops. Now, remember that combinational loops can be handled by event driven simulation, because it is just going one gate at a time, it is propagating the events, and the events might come back also to the input of the circuit through the loop, and you again propagate the events and you can continue this thing. Now there is a problem that if the circuit does not stabilize, then you will keep on generating events, for which we use tricks like terminating the simulation when you see that you are not making progress after some amount of time. But you can handle these kinds of things in event driven simulation, because the circuit might stabilize and then after some time you will see that there are no more events. But how do you handle that in cycle simulation? Because in cycle simulation you want to find out the steady state of the circuit, simulate it once and reach the next steady state of the circuit. But simulating it once is not going to take you to the steady state if you have combinational loops, right? So how are we going to handle that? So the solution to that is encapsulate the combinational loops in macro models. So the macro models are simulated with an event driven simulator, and the circuit with the macro models is simulated with a cycle simulator. So the idea is like this, that we have in this circuit, suppose there are some portions where you have combinational loops, right? The rest of the circuit does not have any combinational loop. So what we do is we take off those portions which have combinational loops and treat them as macro blocks, right? When there is an input, when we want to simulate this, what are we going to do? We are going to take this in cycle based simulation, we will topologically order them. So in the topological order, these macro gates will also be taken into account. Now when we come to the stage where we want to simulate one of these macro gates, we have by virtue of the cycle based simulation, these have already reached their steady state values, because in cycle based simulation we are going level by level. So we have finished off this level, so we have the steady state values here, let us say 1 here and 0 here. So we take that value and use event driven simulation within this block until the output stabilizes to some value, right. So the event driven simulation can go round and round, round and round within this block until it stabilizes. Once the output becomes available, steady state output becomes available, again the simulation proceeds as in cycle based simulation. Similarly, when we simulate this, then we simulate this using event driven simulation, and when the output becomes available, then from here again we do cycle based simulation. So after this level, again we follow cycle simulation. Is that clear? So the main problem here is to find and isolate the combinational loops. Now in terms of graph theory, this is referred to as finding the strongly connected components, in the graph. So this is an algorithm for finding out the strongly connected components. Before we go into the algorithm, let me go through an example, right. So then we will understand what this is. So again we are going to look at the circuit graph. We are going to treat the circuit as a graph where each of the nodes, each of the gates, etc., are nodes of the graph, right. And if the output of one gate is feeding to the input of another gate, then we have an edge from the first node to the latter node. So let us look at an example for this. So suppose so these nodes are the gates, and the edges indicate that the output of one gate is feeding into another gate. Let me number these. Let's say A, B, now first thing that we are going to do is we will start by doing a DFS on this graph. Okay, we will do a depth first traversal on this graph. So let us start the depth first traversal. So remember that for depth first traversal we will have a entry number and an exit number like we did previously. So suppose we start from F. Okay, so this is going to have the entry number 1, right? From that, suppose we go to E. So this is going to have entry number 2. From there we will go to G. We are going depth first, okay, from here to here, then from here to here. Now here again, do we have the only choice is to go back to F, but then F is already visited, so we backtrack and put this exit number as 4, right? Then we come back here. Is there any other place to go from here? No, no more outgoing edges. So this one will have exit number 5, right? Then we go back here. Any other place to go from here? No. So we put the exit number as 6, right? Then we will have to start again from some node which is not visited. Let us say we start from D. So this is going to have entry number 7, right? Then from here we have two choices, we can go here or we can go here. Let's say we first take this one. So then this is going to have entry number 8. From here, if we go here, we find it's already visited. If we go here, it is already visited. If we go here, well, it's not visited, right? So this is 9. Then from here, if we try this one, it's already visited, so there is no other place to go, so the exit number of this becomes 10. Then we come back here, there is no other outgoing edges, so this one becomes 11. Then we backtrace from here. Any other place to go from here? Yes, we can go to B, so this is 12, right? From this, any other place to go? Yes, we can go here, so this is 13. From 13, if we try this, already visited, so no other place to go, so 14. This is the exit number is 14. We backtrace here. When we backtrace here, we try this one, already visited. We try this one, it is already visited, so no other place to go, so this becomes 15, exit number 15. Then we backtrack here, and then from this also no other place to go, so exit number is 16. All right. So this completes the DFS, right? Now what we are going to do is the following thing, that we will reverse all the edges of the graph. We will reverse all the edges of the graph, right? So this edge now becomes this, right. This becomes this. This one becomes like this, like this. Done. Now what we will do is we will start from this, the largest number, the one which has the largest exit number, and we will do a depth first traversal starting from that one on the reversed graph. So let us see which are the nodes that are getting visited by this depth first traversal. So we start with D. So D, then from this on the reverse nodes we are going to have A, because we follow this one, this red edge. Then from A we can go here H, right. From this along the reverse edge we come back to D, already visited, so backtrack to A. Then any other place to go from here, A to B, because this is a red edge, so B. All red edges to B are incoming edges on this side. The only one which is outgoing is this one, but then D is already visited. So the depth first tree starting from the largest exit numbered node consists of these 4 vertices, right. So we say that this set of nodes forms one strongly connected component, right. Then look at the next largest numbered exit numbered node. Which is the next largest exit numbered node? This one, C, right. So we start from C. Where can we go? This one, which is already visited, so we can't do anything about that, and there is nothing else. So this becomes our second strongly connected component. Then look at the next largest numbered ones, which is the one F, right, because it has the exit number 6. So start from F. What is the, where can we go from F? Along the red edges. This one is already visited, we can go to G. From G we can go to E, right. That's it, right. So this becomes our third strongly connected component. Now is this clear that what exactly are our strongly connected components, that how we find them? Now this is the algorithm. You have to understand that why does it give us the strongly connected components, right. Now intuitively you see that what is the exit number of a node? Exit number, you are giving the exit number when you have visited all the nodes that you could from that node and then come back, right. So everything that was reachable from that, so if you take the largest exit numbered nodes, then whatever you could reach from that, its exit number is larger than that, right. And the point is that from which one of those can you reach back to yourself? They are part of the strongly connected components. If you can reach some node but there is no way to come back from that node, then it is not a strongly connected component. So I need to see not only I reach out to those nodes, and then if there is a way for coming back from those nodes, then they all form, they are part of the strongly connected component, right. Now, if there is a way to come back from those nodes, then what is it going to look like in the reverse graph? In the reverse graph, I should be able to go to those nodes along the path through which I came back, right. That is why I reverse the graph and do the DFS, but I always start with the largest numbered node, because I know that from that everything else that could be reached was reached, right. Give some more thought to this, and hopefully you will be able to figure out that why this algorithm is going to work. We can have some questions in the tests, of course, to test whether you have really understood the algorithm or not, right. So, that is how you find out the strongly connected component. Please look at this slide which talks about the formal algorithm for this, right. And with this we also come to the end of the chapter on simulators. Thank you.